like Zoom provides this new sound effect. All right. So we will talk about two parts today. We will first spend some time on the remaining 6 or 7 slides for the growth of function. And we basically have covered 3 types of notations from big theta to big omega and big O. Okay, so the relationships between these 3 types of asymptotic properties can be described mathematically. And actually, the easiest way is to use graphs, to use the figures in which functions are bounded by the upper limits, the upper bound, the lower bound. So for that graph, I will show again at the end of these slides, which I think is the best way to memorize these 3 types of notations. And before that, we will cover these 2 last types of notations, which are first one, the small o, okay? And we can guess that it must be related to the big O, okay? So the difference is that we can use the big O notation to describe a upper bound that is asymptotically tight, okay? But the small o notation, oops, I just noticed the typo here. Let me fix it really quick. Okay. Share the screen again. All right, so the difference is that when we use a small, it refers to basically an upper bound, but it's not necessarily a tight upper bound. It can be a very loose one, okay? So if we look at the definition for small o, okay, and we compare it, it says, the definition is right here, okay? So it reads quite similar to the big O notation, but I highlighted the different part here. It says for any positive constant C, there is a constant n0 such that the function is bounded by this C times G of n, okay? So the difference is that in small o, we ask this constraint, this inequality, to be satisfied for any positive constants. So this is a very strong condition, which says that it doesn't matter how small C can be, the C times G of n is always the upper bound. Okay, so intuitively, if we think of it intuitively, like then the G of n must be a very big function. Okay, so it is likely to be a very loose upper bound, not a tight upper bound. All right. So the difference, as I highlighted here, the big O asks this inequality to hold for some constants. Okay, and we in order to prove the big O notation, all we need to do is to find some constants. But for the small o notation, we should prove that it applies to all the constants. So which is essentially a different question, and which is also much harder. Okay, so I would say in our most common cases, we want to use small o as a common practice, as a common usage, and the big O is much more frequently used to describe the asymptotic properties for functions, especially for algorithms. Okay. All right. So, but I think it's still useful to look at the differences. Okay. So If we describe the small o notation, use the language of limits, then we can say that the function f of n will become insignificant or insignificantly small relative to g of n if the n increases when n approaches infinity. So if we describe it in the equation that you use the limits symbol, it will be like this. So the function f of n will be really small when n grows approaches infinity. Okay, so that is a small o notation, and now we can look at the small omega in parallel. So it's basically the same relationship as small o is to big O. It is just a lower bound that is not asymptotically tight as compared to big omega. Okay, so it could be a very loose bound, and it also requires that for any positive constant, it's always the lower bound for the function f of n. Okay, and if we describe it with the limits language, it basically says that when n approaches infinity, then g of n will be really small compared to f of n, which leads to the ratio of fn over g of n approaches infinity, okay, which is basically the opposite of the small o notation. Okay. Okay, so another example that I didn't show in the previous slide is that if we look at this quadratic function example, okay, so we can say that this quadratic function, which is n squared over 2, we can say that a linear function is a loose upper bound of a quadratic function, right? So this small omega indicates that the inside n linear line is a loose lower bound for quadratic function, which makes sense, right? Because if you draw a quadratic function, it will increase much faster than a linear line. But we cannot say that another quadratic function is the loose upper bound, okay? Because we cannot guarantee that for any constant c that one quadratic function is always smaller than the other, okay? Because they basically have the same growth rates. They are all quadratic terms, okay? And that's for small omega notation, okay? So we can basically memorize their relationship in parallel with the big O and big omega, but they only represent a much more loose upper bound and lower bound. Okay, and then in the next slide, let's look at the notation, the asymptotic notations in equations. Okay, so the usage of these notations are to first to represent some anonymous function that we do not care to name. Okay, for example, we can say that the worst case running time for merge sort is can be described by this recurrence, and we know that the cost for dividing the input sequence and the cost to combine the two parts of the sorting result is a linear function. But if we don't want to define some constant to write a very specific linear function, we can just use big zeta of n to indicate any kind of anonymous linear function. Okay, so it basically means that actually the f of n here is in the set of big zeta of n. Okay, that's the most common usage actually, and these notations we can actually put them on both sides of the equations. And the example I showed here, it says that, let me highlight it with the color here. Okay, it says that 2 times n squared plus big theta of n equals big theta of n squared. So it basically describes the principle or the relationship that we actually used before. It basically describes the principle that we can ignore the lower order terms compared to the highest order term. On the left, the combination has two components: the higher order term, which is a quadratic term, and the lower order term, which is a linear term. And if we use the equal symbol to connect the right and the left and right, it basically means that compared to the quadratic term 2 times n squared, the linear term can be ignored. And no matter how this linear term changes, it can be 2 times n, it can be 4 times n, it can be any number times n. No matter how it changes, we can always find a quadratic term. We can always rewrite a quadratic term that grows as fast as the left side. Okay. So it basically says that we can basically represent the left side with some anonymous quadratic functions. Okay. And that's basically the second usage. And another more flexible usage is that we can chain the equations, which is similar to the case above. So it basically we can ignore the lower order terms in the equations. So if we look at the constant term here, this one can be actually written as big theta of 1, right? And this 3n plus the constant can be simplified into big theta of n, right? And furthermore, we can also ignore the linear term and use only the quadratic term left. That's the common usage of asymptotic notations in equations. Okay. And then speaking of the relational properties of those Greek letters, we can summarize them, use some theorem or principles. First, it's called transitivity. Okay. So it basically says, in terms of big theta, if we have three functions, and the g of n is a tight bound for f of n, and the h of n is the tight bound for g of n, then we can infer that the h of n is also the tight bound for f of n. And the same principle applies to the big O and the big omega, small omega, and the small o notations. Okay, so I think it would be easier if we use the analogy to compare the real numbers. If it's the first time we come across these Greek letters, it will be easier to memorize if we use this analogy. For example, the big theta basically says that the f can be sandwiched by g of n, which basically means that they grow as fast, they grow at the same rate, with the same speed. So we can use like a equals b to describe this equal relationship. Okay, and the big O on the other side means that we are describing some upper bound. Then if f of n equals big O of g of n, which basically means g of n is above f of n, right? Then we can use f of n is smaller than or equal to the other function. Use this smaller than, less than or equal to relationship. So, and big O and small omega, which basically means a more strict less than or equal to relationship, because they are describing the loose upper bound and the loose lower bound, okay, which is a more rare case actually. Okay, and I think we have several slides to cover the relational properties. All right. So reflex civity basically says that one function is the tight bound, and no matter upper or lower bounds of itself. Okay, and symmetry basically says that the one function is the tight bound for the other if and only if the opposite relationship also matters, also matches. Okay, and the transpose symmetry basically describes the supplementary relationship between big O and big omega. And one function is the upper bound for the other only if the other one is the lower bound. I think all these relationships quite make sense. Okay. All right, so lastly, let's look at some common functions. I think these will be more useful if we know about the symptotic bounds for some common functions. So first of all, two types of functions that we're gonna really use quite often in this class. First, exponential function, okay? And this type of exponential function has a base that is greater than 1, okay? Because if a base is, say, 0.5, then it is a decreasing function, right? Which is not of our interest here. So for any exponential functions that has a base that's greater than 1, then it's always grows faster than any polynomial function. Okay, this is something we want to keep in mind. Okay, because when we design algorithms, no matter how fast it no matter how small the base is, as long as it's greater than 1, then it is not good news for us because it grows really fast. Okay, so we can say that the exponential function here, which is a to the power of n, this is exponential function, and a is greater than 1. It's a loose upper bound for any polynomial function. And in the left, n to the power b, this b is a constant, and this b can be a really big one, okay, like n to the power of 1,000, okay? And even if a is 1.001, then this 1.001 to the power of n, this exponential function, it may have very small values at the beginning, but as n grows, the increased speed is really fast. It's even faster than this n to the power of 1,000. Okay, so it means that we want to basically avoid exponential functions when we choose algorithms, when we design algorithms. Okay, so in the language of limits, we can say that if we use the ratio, if we consider the ratio of a polynomial term over the exponential term, then the limit of it will approach 0 if the input is approaching infinity. Okay, so this relationship is something we will use in the following property. Okay, so the following property says that it's basically an inference from the above one. It says that any positive polynomial function grows faster than any, we have a new term here, than any polylogarithmic function. It's basically a combination of polynomial and the logarithm. Okay, it's basically said that the polynomial function is faster than the polylogarithm function. Okay, the polylogarithmic function says that it's basically in this form. It's the logarithm of the inputs raised to the power of some constant k. Okay, so it's the logarithm first, raised to the power of k. So this is some information we will need to use when we compare the efficiency of algorithms. So it basically, to put it simple, we can say that if the efficiency of an algorithm, if the running time of an algorithm can be described by a mathematical term that has some logarithm terms in it, then it's good news for us, okay? Because the polylogarithmic function grows slower than any polynomial functions, okay? And the polynomial functions, including quadratic functions, cubic functions, are sometimes we don't consider as the most efficient algorithms. Okay, and this actually can be proven from the property above in the blue color. Okay, so we can replace do the substitution by replacing logarithm n for n and 2 to the power of a for a into the above terms, the limit terms, and we will have this new limit. Okay, and the denominator becomes a polynomial function, n to the power of a, and the numerator is a logarithmic term. So it basically says that the numerator will become insignificant as n increases. Okay, I think these are the most important two properties for common functions. And on the next slide, I think it's the last slide, it says we'll look at the factorial functions. Okay, so the factorial, it actually has a pretty loose bound of n to the power of n. Okay, so this is even even higher upper bounds as compared to the exponential functions. So we basically can see that the factorial function is not is a function that grows really big, and also grows really quick. So, and even we compared this factorial function with the exponential terms, we can see that the exponential term is a loose lower bound for the factorial. Okay, and if we take the logarithm of the factorial, we will basically have a tight bounds defined by n times logarithm of n. Okay, so again, we don't need to know exactly why this is the case, but all we need to keep in mind is that factorial is something that's even worse than the exponential term in terms of the growth rate, in terms of how fast they grow. So in algorithms, we definitely want to avoid such cases that the running time are in factorial time. All right. So in the last slide, we basically describes these three types of relationships in the uppercase Greek letter notations, and big theta describes the tight bound. F of n is somewhere in between the lower bound and the upper bound. And big O is just to describe the upper bound, and big omega is to describe the lower bound. I think the most important thing is that we keep in mind of these relationships between functions. All right, so let me stop the recording.